Hey, physics. Back at it, right? This is going to be a little bit strange. It's going to be a longer video than usual, but it should be posted to YouTube as well as my CVA. The YouTube version is nice because it has timestamps and you can go directly to the part that you're interested in. So I'm going to start here on this. I'm on the PHET website, that simulations website again. We're going to start here. And then I have some definitions and stuff, and then we have some math and stuff to do, but we'll take this kind of, like, not slow-ish, but this is, all the stuff that we're doing in class. I have a simulation version of it, and then the definitions are what they are. We'll get into some examples. There will be three sets of examples. No, probably two sets of examples and then a quiz. Maybe three. You know what? Probably let's say three sets of examples and a quiz. But yeah, so waves. Waves are actually the last topic that I want to talk about. Um, One of the nice things about waves is again, well, actually, one of the nice things about physics in general, at least in my opinion, over chemistry, is it's all visible for the most part. Waves are nice because you can see them. Like if I, this simulation, by the way, is wave on a string. So here's a string, and here comes the wave. Right. So there's a wavy thing. Um, right now it's kind of like fixed in place. So in class, what I did, I had just had somebody sitting on the floor, and then I sat on the floor in the back of the room, stretched out a real long slinky, sitting on the ground, and I shook it back and forth like this, and I made a wave, and it did kind of interesting things. There are some things down here. If you're curious, if you want to look at what this is the wave on, like, again, PHET Colorado.edu. Um, Simulations, physics. This one's wave on a string. There are different options. I'll go through those in a moment. Right now, the important thing that's on right now is this thing called damping. Basically, it's friction. It's friction on a wave. Because when we were in the classroom, I was moving the slinky back and forth on the ground. The slinky was touching the ground, so there was dampening. So what I said was usually you see waves and they kind of look like this. And that's kind of a wavy pattern. You should notice that it is bigger down by the where I'm actually making the wave, by the wrench part, and the reason for that was because of the friction between the spring and the ground. Right. In this case, it's because of the damping. The damping option is turned on. I'll turn that off eventually, but not yet. Not right now. Um, Now this is nice because it's not quite exactly like a sine or a cosine curve. Like if I wanted to, I could just make an actual regular kind of really, really nice pattern here, right? So this is a pretty nice pattern. It's big on this side, it's small on the other side, and that has to do with friction. We're losing energy to the ground. In the classroom, you could also hear the slinky going back and forth, so you're losing energy to sound as well. But generally speaking, and let me actually just bump this amplitude up so it's easier to see. You should be able to see kind of an interesting pattern here. If do I want to go with oscillate? I think I'm going to go back to manual for a second. If I try to do this reasonably consistently, you should see one, two, three, four, I think four up and down pieces of the wave. You're kind of, again, maybe I'll just go back to the oscillating because it'll be simpler that way. It goes up, down, up, down, up, down. It ends up hitting the end and it'll spit back. But each of these, right, it's bigger on this side than it is on this side. And again, I'm using the term like wavy thing, which is very technical. The crest at the top or the trough at the bottom, it's bigger at the beginning of the wave than it is down here at the end. And the reason for that, or the explanation of the size of the wave, it's called the amplitude, right? So that's what this is down here. The amplitude of the wave is literally how big is the wave. If I increase this, the wave gets larger. If I make it smaller, then the wave gets smaller. Oh, I killed it entirely. But yeah, so there. So the amplitude is the up-down height, right? The height from the center point to the tallest part, or the center point to the lowest part. That's what we call the amplitude. This frequency is kind of commonly mistaken for speed, for how fast it is. it's not specifically how fast the wave is going. Frequency is how many waves at a time do you see. Right now it's set to 1.5 hertz, 1.5 hertz. Hertz is a unit of frequency. Frequency is really how many waves go by in a second. So what this is saying is that 1.5 waves goes by every second. If I decrease the frequency, you should notice, oh, not that much. Don't do that. Well, let's decrease it to let's decrease it to half. So this is half of a wave goes by every second. You should notice it looks like it's going slower. It's a little bit of a misnomer. Waves do have a speed, and it's related to their frequency, but it's not exactly their frequency. So the frequency of a wave tells you how many waves go by in a second. If I bump it up to, almost, let's say 2.5. So this is 2.5 waves are going by every second. And you can kind of see there's one that's an up and down, and then two, it's another up and down, and then there's a half. Right? One wave is like one sine or one cosine wave. This is 2.5. If I make the frequency 1 and I get rid of the damping, what you'll end up seeing is basically a single, this is kind of a cosine curve, but it's a single, oh, hang on. Let me stop everything. How do I stop? Turn all the damping on. Alright. Oh, too bad I can't exactly bring it to 1 right away. Oh. Oh, that's interesting. I should do this. It's close. It's still wobbling a little bit. What's happening right now is kind of interesting. It's something I did during class too. It's a little harder on the simulation. I was playing with it earlier and I couldn't quite figure out how to do it. Now this is an interesting way to do it. What's happening is I'm trying to put a 1 hertz frequency wave on the line, but there was still a little bit of wave happening. So what's happening is that those two patterns, the old frequency wave and the new frequency wave, are kind of overlapping with each other and they're interfering, right? So waves interfere with each other because waves are just energy. They are a transfer of energy from one spot to another spot. Often they need to go through stuff, but waves are just energy. I wonder if I... Oh no, that didn't help at all. Please stop that. Just gonna hit reset. Waves transfer energy from one place to another place, and the easier way to see the overlap, that interference between them, is actually by doing something with pulses. Now usually when you see waves, you see whole waves, but what you might see instead is just a wave pulse. Alright, and this is a wave pulse. It's not a great example because you don't usually see like triangle waves rolling around, but here is a wave pulse, and you should notice what's happening. It's traveling forever because the damping is completely off. There's zero friction. We're not losing any energy to anything ever. I started it goes up, and then it hits the barrier and it goes down, and then it hits the barrier and it goes up, hits the barrier and it goes down. All right. Now I can make another exactly the same wave pulse, and it's a little weird. It's hard to tell what's happening. It might look like they're kind of like bouncing off each other, but what they're doing is they're passing through each other. Right? This one that's on top is always, so here's this one. It's up, and they overlap, and it's up, and then it hits the barrier, and it's down, and they overlap, but it's still down. What's even more interesting is that when they overlap, there actually comes a point where you don't see anything. They interfere so much with each other that they disappear temporarily. They'll be back. So again, I have one on the top, it's going this way, and I have one on the bottom, it's going the other way. If I go frame by frame, you'll see that the one on top is continuing to the right. It's trying to continue to the right. The one on the bottom is there. That these this thing is still going to the right, and the bottom one is still going to the left. And what you'll see is that after they disappear, the first thing that happens is, oh look, something is appearing going to the right on the top. Something is appearing going to the left on the bottom. Right, I'm going to turn the dampening on again for a second because I want them to die out. Right. Interference has two versions, constructive and destructive. I have to time this. How do I time this? Oh, this is hard. Alright, I think that worked. This is actually two waves. I'm going to try to add another one. Yeah. I just kept doing pulses. I did another pulse. They started out with an amplitude of 1.25 centimeters, and if you look, it's very clearly more. I'll leave this on 1. 1.25 centimeters would be right here. It's way higher than that now, because they are interfering, they overlap with each other. You can get more than one wave pattern to exist in the same space as another wave pattern. In this case, I'm just using pulses. Let me turn the dampening back on and turn the wave off for a second. Go away. Oh, normal speed. There we go. Alright. If I do it here, I'm only doing slow motion so that you can see. This is... there. 1.25. Yep, that's 1.25 centimeters. Right. If I time it to make another wave, right when this thing goes by, bang. It should be about it should be about 2.5. Now, did I time it perfectly? Clearly not. Because this is 2.25. So I missed it just by that much. I missed a perfect overlap, because a perfect overlap should be 1.25 and another 1.25, which is 2.5. So I missed it by a little bit, but they overlap just enough that they add on to each other, right? Waves interfere with each other one of two ways. Constructively or destructively. Right now, here's the better version. This wave down here is almost a little more than 2 centimeters. It's almost exactly 2 centimeters. This wave up here, we know should be 1.25. Now, oh, sorry, that's 0. Yep, so that's about 1.25. This one is, right, 2.25. Or just a little over 2. Now what should happen is when they overlap, a little over 2 minus 1.25 is a little over 1. There it is. There's the overlap. Notice the bigger one goes down, the smaller one goes up, so most of the wave was still pointing down. If I let this go again, I'll let them overlap when the bigger one's up top. So here it is. The bigger one is up top. I want this thing to go away. I don't want you. The bigger one is up top. It's 2.2. Smaller one is on the bottom. It is 1.25. So a perfect overlap should be 1.05, right? 2.2 minus 1.25, I think. Or 0.95. It's just under 1. Right, so here they are. They're about to overlap. As they overlap, you'll notice that the big wave on top gets pulled down by the amount that the smaller wave is. And it is just over 1 centimeter, which is, again, what we expected. And as I keep going, that big wave on top continues on. And this is also how I know waves travel through each other and they don't bounce off each other. Because that bigger wave is still up top. And the smaller wave is still on the bottom. And I can let them go on indefinitely. If I add a third one to the mix, you start to see some really interesting things happen. And what I could do, I'll bring it back to normal speed. The trick behind a wave is that it's just a bunch of wave pulses that continue to happen. And depending on what interference you set with them, they will just go. Right? Now this is like freaking out a little bit. Or reference. Oh. What is that reference line? Is that reference line 1.25? I'll bet it is. Oh, no, it's not. It's just a reference line. That's interesting. Now, wave interference is like a key concept because it's responsible for most of the interactions that we have. Waves interfere constructively very frequently. The amplitude of a wave, what you saw, that peak or the crest, right, is what I called it before, or the trough, that bottom part, that amplitude is the brightness of light or the loudness of sound. So wave interference is responsible for making bright things brighter or loud things louder. It's very rare that interference happens destructively in real life, in regular, I should say in regular life, like real life is a little harsh, but in regular life. You have to go out of your way to make destructive interference. And the best example is actually a set of headphones that are noise canceling. Noise canceling headphones are pretty unique. I have a set. So these noise canceling headphones have a little switch. If I flip the switch, it turns on noise canceling. What you should notice about all noise canceling headphones is that there is this little opening here on this side and an identical opening here on the other side. Those are small microphones. And what they do is they wait and they listen for outside ambient noise. They listen for these. They listen for this from the outside world. They look for this background noise pattern. All sound is waves. So those microphones just listen for that outside background noise. Right? And what the noise canceling technology does is it listens for this and it makes this. So that when your ear, by the time the whole wave gets to your ear, you hear this. You don't hear that background noise because the headphones send out, in addition to the music or the show or whatever it is you're listening to, it's also sending out this other wave. And that wave is designed to cancel out the outside world. Now, in real life, noise canceling headphones don't do it perfectly like this. In real life, what noise canceling headphones do is they'll do something like this, where they will bring the noise down to that much. So instead of hearing the full effect of the background noise, you get a much smaller effect. And the reason for that isn't because we don't have the technology, we aren't able to cancel out noise perfectly. It's because that limited background noise, it's like a safety feature, right? You don't want perfectly noise canceling headphones because then all you would hear is whatever's in your headphones, which is pretty unfortunate if the person next to you or behind you is, or there's a yelling at you to not step into the road because there's a car coming. You don't hear stuff. You become less aware of the world around you. So safety precaution. All right. But noise canceling headphones are a prime example of destructive interference. So waves, they interfere with each other. Depending on the interference pattern, you can make a wave that's much bigger. You can make a wave that's slightly bigger, or you can make a wave that is just a boatload of nonsense. Right? Some wave patterns look really nice. Some wave patterns look less nice. All right? For a little bit, this looks nice, and then it looks less nice, and then it looks nice again, then it looks less nice. That's all, and then it goes away, right? Those are all examples of how this is interfering with each other. You should remember that this wave goes over, and it bounces back. And when it bounces back, it's going to interfere with what this is generating, and eventually, over time, it will all cancel each other out perfectly. take some time to get there. But wave interference. All right. Let's see. Okay. Now, not all waves move like this. Right? Many waves move. Well, okay. Let's reset some stuff. Not all waves move like this, right? Light waves, if you could see other than just like, oh, it's bright. If you could see the actual shape of a light wave, it would look something like that, right? It would be that traditional up-down wave. Sound waves don't quite look like this. Sound waves look like... I wonder... There isn't a version of it. That's interesting. I'm surprised they don't have one for this. Maybe they do. Maybe the wave interference one does. Wave interference. No. Doesn't look like that. Reset. Not a great example. If you think of a slinky, you can take the slinky and you move the end like this so that it'll do that, or you can pull the slinky and let it go and it'll ripple back and forth on itself. That's what a sound wave looks like. It's a compression wave. I think of it kind of like a pressure wave. It moves a little differently, and the only reason I bring that up is that your sense of hearing and your sense of sight are based on the two different things. Sight is based on being able to see this pattern. Sound is being able to detect this pattern in the air. Anyway, I'm just going to pull this up again, but got my whiteboard back. I'm going to mention something about some wave definitions here, because there are some things about waves that you should be fairly familiar with. You should recognize on some level if you were asked to identify something. So, oh, that looks terrible. Can I? Is there a shape thing here? No, there's not. All right, we're gonna pretend like those are one continuous, nice-looking thing. The distance between here and here, right, from center to the top, or the center to the bottom, both of those are the amplitude. And again, that's most commonly associated with the strength of the wave. It's brightness for light, it's loudness for sound. The distance from here to here, right, for one up-down section, or from top to top, so here to here, or from bottom to bottom, so from here to here, all of those are considered one wavelength. Right, literally the length of one wave. It's measured in meters usually, and there's a symbol for it. It's kind of funny. It's lambda. It's a Greek letter, another Greek letter. Sorry, but it is the literal length of one wave pattern. So again, a full top and bottom, or top to top, or bottom to bottom, however you can measure that, depending on what picture you have. So length of one wave. It's a length, so again, it's measured in meters. Making a second picture just to make sure that things are slightly, pretty clean. All right, I made two different kind of wave patterns here. One of them is this big one, and one of them is this slightly smaller one. Right, I was doing really well until that last fourth there. If, let's say that this was, I don't know, this is just a height, and this was time. And this is time equals 0 all the way over here, and this is time equals 1. This is 1 second, so time in seconds. So let's say that this is 1 second right here, right? The frequency of a wave is something else you should be familiar with, right? And I said before, it's not like the speed of the wave, but it's like how many waves. Specifically, it's how many waves in 1 second. How many waves pass in 1 second? It's measured in hertz. It could also be measured in 1/seconds. It's very rare that you'll see 1/seconds, but if you see something in 1/seconds, that's a frequency. They're telling you how many times did that wave go by. If I call this wave A and I call this wave B, wave A has a frequency of 1 hertz. Wave B has a frequency of 2 hertz. I want you to notice something about a potential relationship between the wavelength and the frequency. Right? And this is something that I can do back over here. I'm going to put the oscillate back on. So here is the frequency is 1.5 hertz. All right? And I want you to look at like how many waves there are, right? What's true about the wavelength? Well, the wavelength is about, well, here is there is a let me hang on. Go back to manual. Can I go into here? Okay. And do this. Man. There's no way to... Okay, there is no way. Let's put the damping back on. Let's restart. Alright. I'm going to increase the frequency. Suddenly. I'll restart it. Frequency went up, and you should be able to see that a wave now is like all the way here, right? If I put the rulers back on. That's about 1 wavelength now, I would say. Just, that's about 1 wavelength, right? At 2.5 hertz. Let me bring it down to 1.5 hertz. And if you look, that's not even close, right? 1 wavelength here is probably all the way out to, I would say, there-ish. I'm guesstimating here, because it's not exact. There is some dampening. There's some damping happening here. But that's about 1 up and down now, right? The wavelength is a lot bigger. If I decrease the frequency even more, if I bring it down to 1 hertz, and the wavelength becomes almost this entire thing, right? Frequency goes down, wavelength goes up. Frequency goes up, wavelength goes down. Right? That is indicative of an inverse relationship. So wavelength and frequency have an inverse relationship. Which basically, again, just as if frequency goes up, wavelength goes down, frequency goes down, wavelength goes up. And that's this little picture here, right? Now, I did also show amplitude was affected here, and you guys probably noticed that amplitude was affected here, right? If I increase the frequency, then the amplitude stays the same here. Never mind. No, that's a bad example. Because this is good. Amplitude is independent. The only way to change the amplitude is to change the actual strength of the wave, right? Now, I'll come back to it. But we got amplitude, we got wavelength, we got frequency. One more thing to keep track of is there's kind of like there's one more little term here before I move into the next set of terms. Actually, I'll do some review of this first, and then I'll move into the next set of terms. There's one more thing related to time, and it's the period of a wave, which is a capital T. Now, frequency is a lowercase f. Period is a capital T. It's measured in seconds. There we go. It's measured in seconds. It's how long does it take for one wave to pass. Right. So I want you to notice for wave A, it takes 1 second. So the frequency for A is 1 hertz. The frequency for B is 1 hertz. The period for A is 1 second. The period for B is 0.5 seconds. Because it takes only half a second for wave B to go by. Look, so here's wave B. That's one full wave. It only took half a second to do that. 2 waves go by in 1 second, so 1 wave would go by in half a second. But this is the other relationship, is that period and frequency also have an inverse relationship. Right? There are really 2 equations, maybe 2.5 equations, but really 2 equations for waves, and that those 2 relationships are the heart of them. This one here, that frequency and period have an inverse relationship, and the one all the way down there in the corner, which is that wavelength and frequency, have an inverse relationship. Anyway, I'm going to do a little bit of review here because it occurs to me that there's almost certainly going to be a homework assignment on some of these definitions, probably all these definitions and the interference stuff. So, quick example looking thing. Let's say that you are given a graph Alright, and say that those are all supposed to overlap with each other fairly well. Let's call this again wave A, call this wave B, we'll call this wave C. Potential questions. You know what? I shouldn't make all of them the same. Let's do this. Let's call this wave A, and let's say that this is 1 second. Right, so this is time in seconds. This is 0, and this is the height of the wave. Let's say that this is 1 meter. And let's also make wave B again. It's going to be good enough. And this is also 1 second. This is time in seconds. And now this is 1 meter, and this is 2 meters. Let's do that. Fairly common, like, comparison, or common just identification, right? Identify the amplitude of both. Identify the frequency of both. And identify the period of both, right? So for both wave A and B, what's the amplitude? What's the frequency? What is the period? Amplitude should be fairly straightforward, right? The amplitude of wave A, and I'll do it this way. So we have A, we have B, make a little table. Amplitude is 1 meter for A. Amplitude is 2 meters for B. The frequency of A is a little funny, right? 1.5 waves go by. Or no, 1.5 waves go by in 1 second. Oh, no, it's not funny. It's not that weird. It's the period. So 1.5 hertz. Because in 1 second, 1.5 waves go by. For B, it's 2 hertz. Because after 1 second, 2 waves go by. The period is a little funny, because period is how long does it take for 1 wave to go by. Well, B is fairly straightforward. B is just, well, it took 1 second for 2 waves to go by. So it'll take 0.5 seconds for half a wave to go by. Here, if it took 1 second for 1.5 to go by, divide 1 by 1.5, right? 1 divided by 1.5, that's 2 over 3. That's 0.67 seconds to get the period. Or it's 2/3 of a second. Because this would, let's figure that the wave is evenly spaced, right? This would probably be 1/3, and this would be 2/3, and this is 1. That's 3 over 3, right? So it takes 2/3 of a second for one wave to go by. That's what the period of wave A is. Again, I hope this seems straightforward enough. These questions are usually fairly straightforward. The tougher ones are the ones that involve... Oh, right, we're still going here. The tougher ones are the ones that involve interference. Wait for that to die. And the reason the tougher ones are the ones that involve interference is because they tend to be harder to visualize. Oh man, that's as small as the pulse width goes. Okay, that's fine. Let's go slow motion. Alright, so, fairly classic question. And I should try to... Ooh, I know what I should try to do, actually. Nope. 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 Okay. I'll wait for it to rebound all the way back. I want to make one that's longer than the other again. Oh, that'll work. Okay. Okay. So here I have, this is going to the right, and this is going to the left, right? So we're going to make that here. I'm going to make a different picture representation of that here. I have small on top. This going up, and I have this going down. This is moving to the left, this is moving to the right. I'll call this wave pulse A, and I'll call this wave pulse B. And a common thing is, what will the interference pattern look like? Right? What will it look like when these two things overlap each other? Now, we've done this, and I showed you this, and oop, missed it by that much. Let's go normal speed again. Oop. Okay. Dang it. Alright, when they interfere, oh look, it's down, but it's not as big as the other one. And that should make sense, hopefully. Right? A is going to continue to move to the right. B is going to continue to move to the left. They will overlap onto each other. So A is up a little bit, B is down quite a bit. When they overlap, A will flatten out, B will get a little shallower. So what will it look like? It should look like this, where it'll end up looking like that. Right. Now, again, I said usually your waves won't be like triangular. More often, they will give you a bubble up and like a bubble down. They'll be about the same. They'll tell you this width and this width will be the same, and they'll be moving towards each other like this. Or they might give you a square or rectangle going up and a rectangle going down, right? And they might do this. Now, the same question though, what will the interference pattern look like? Well, from here to here is 1, and from here to here is 2, right? When they overlap, if they're overlapping oppositely, you subtract them, and whichever one is bigger, it goes that way. If you have this and this, and again, they're both coming towards each other, let's say that this height is 1 and this height is also 1. That's constructive interference. They're coming at each other, 1 and 1 on the same side. It's going to be 2 on the same side, and I showed you that one on the other side too. All right. Interference patterns are the funniest ones, or the strangest questions to kind of go through. Weird ones to look at, but totally doable. They're just a little funny. All right. Now, couple other possibly interesting definitions to kind of look at and try to wrap your head around, right? Waves can interact with each other, right? And that's this phenomena, where this is wave interference. They actually interfere with each other. Waves can also interact with a boundary, right? And if I restart this, you see that it's on top, and then it bounces on the bottom, bounces on top, bounces on the bottom, all right? And that bouncing has a name, which you are very familiar with. So we have these other wave interactions. The first interaction that I want to talk about is wave reflection, right? And this is something very common, right? Mirrors reflect light. You can create a reflection pattern. Windows can reflect light depending on the angle that you're at. But reflection is what happens when a wave reaches, I'm going to use the word reaches, when a wave reaches a boundary and bounces off, right? So literally, I'll make the boundary like this. Okay? Literally, if this is a wave, and I'm simplifying the wave just so that I don't have to draw the squiggle back and forth, reflection is what happens when it simply bounces, right? Now, an important thing about reflection is that if you make like a 90-degree angle to the point of reflection, this angle here, which is the initial angle or the angle of incidence, and this angle here, how come you didn't make that a circle? All right, whatever. This is the angle of reflection, that's the reflected angle. They're going to be the same. When a wave bounces off a surface and it reflects, that angle stays exactly the same. All right, and this is an important concept for visual fields, particularly for driving. More on that in a moment, because there's another wave interaction that also starts with an R and is kind of similar. There's also wave refraction. I realize that I should make sure that my letters are fairly clear here. Wave refraction is what happens when a wave reaches a boundary and bends through, right? Now, reflection is something that you experience in mirrors. Refraction is something that you would experience much more commonly with water. If anyone has a fish tank, and you've ever tried to reach into the fish tank and you like think you're in line, and then you suddenly miss and you have to like adjust, and it's like, oh, it's way further than I thought, or oh, it's way closer than I thought. It's because of refraction. Your eyes work off of light coming in because it's reflected off of a surface. Right, so the reason that you can see stuff is because the light reflects off of it, that light bounces into your eyeballs process the information in your brain is like, that is a thing right there in that space. When we use mirrors, we use a secondary reflection. So the image of the object is reflected off of the mirror and then into our eyeball. Our brain is like, oh, it is actually over here because it's reflecting off of that mirror, so I should reach here, right? Refraction works a little differently. What it does, let's say you have a wave that comes like this. Well, instead of going straight through as you would expect it to, it will bend, right? And again, if I make my like imaginary thing, right, here is this time I'm just going to call it angle 1, and this is angle 2. There is a relationship between angle 1 and angle 2, which I will get into a little bit later when I talk more about equations. But for right now, refraction is what happens when a wave reaches a boundary and it bends through. So just like identifying which one is which. Reflection bounces, refraction bends. All right. I'll talk about a third one that also starts with an R. And this has more to do with sound than it does with light. These two interactions are typically light. The sound interaction, again, also starts with an R. It's called resonance. And this is when an object, yeah, that's not how you spell natural. When an object vibrates at its natural frequency. All right, and there's a little bit more of a story behind this one. So let's take a second here and talk about this. I say let's. I'm going to take a second here and talk about this. Resonance is something that you have all probably experienced at some point, especially if you've ever been to any kind of restaurant that has like nice glassware, and you Should it work with this? No, it doesn't work with this. If you do it with glass, right? You take your finger, dip it in the water, and you go around the rim of the glass. You hear a noise, right? You hear a sound. You hear a note, and that note is the natural frequency for that glass. Now, technically, you can change the frequency by filling it a little bit with water. If you've seen those street performers with the bowls of water or the glasses of water, and they take their hands and they play a song with it, they're playing with the resonant frequency of the glass. You've also probably seen videos of people who can shatter glasses. Usually it's like an opera singer. They'll sing a very high note, and the glass will just shatter. And you might think, it's just because they're loud. Like, if you shout loud enough, any glass will break. You can do a lot easier with the resonant frequency. All objects have a natural frequency that they vibrate at. All objects have a note that they play, right? Frequency, when it comes to sound, is the pitch of the sound. High frequency is a high pitch. It hurts your ears more, so frequency is measured in hertz. High frequency, more hertz, hurts your ears. Anyway, every object has its own natural frequency, and if you play that frequency loud enough, the air molecules are moving at that wavelength, at that frequency. The object will start to move on its own at that same frequency, which is what happens with the singer in the glass. This also used to happen with soldiers when they would march in formation over bridges. They march in formation. Every soldier is stepping at the same time. They make a certain frequency. If the frequency matched the frequency of the bridge would shake along with the soldiers as they marched, and the bridge would collapse. Not under the weight of the soldiers. It was perfectly capable of holding the soldiers had they been standing still. But the fact that the soldiers were marching in time, that was what caused the bridge to collapse. This can also happen with like wind patterns, depending on the sturdiness. But if a wind pattern can create the correct frequency of swinging for a bridge, then the bridge will sway back and forth, and it will do so much more dramatically. You can do this with a building too, with an earthquake. Earthquakes have a natural frequency. They send pressure waves through the earth. Not everything is compressible, so it will make the earthquake like a wave. Now, if that wave pattern matches the pattern that a building would want to shake at, it will shake much more violently and it will collapse. So architects and structural engineers in areas with lots of seismic activity have to keep that in mind. They need to be careful of what is the typical frequency of an earthquake, or what frequencies could be avoided in order to build these structures. Now, resonance is something that's typically associated with waves, but resonance is specific to the natural frequency of an object. You can do this if you have a tuning fork and you play it loud enough, you can get a guitar string or a piano string to vibrate at that exact tone. You can also do it just with a guitar. The top and bottom strings of a guitar are tuned to the same note. They're not exactly the same frequency. I am cheating a little bit here. But they are the same note in different octaves, and those frequencies are related because they actually look like this. Oh, hang on. They look like this. The large string looks like this. The small string wave pattern looks like this. They match just well enough in the air that if you strum the top string, and you strum it big and loud, and then you stop only the top string, you should be able to still hear tones being played, and that was the resonance from the air that the top string moved, causing the other strings to move. The other strings move a little more or less because it's not exactly their natural frequency. Oh, actually, you know what? The most common place you probably heard resonance, or like experience resonance. Sitting in the car listening to music, if you listen to it pretty loud and you have like random objects in your car doors on certain notes, sometimes it's bass notes, actually a lot of times it's bass notes because they cause a lot of vibration. But you hear those random objects rattle under certain notes or certain parts of songs. That's because the resonant frequency of your car doors is very specific, and if a song hits it and it hits it loud enough, it will cause the doors to actually shake, which causes whatever's in the car door to rattle around obnoxiously. But yeah, so we got resonance too. Now, yeah, these phenomena are, again, interesting. Reflection, refraction typically deal with light, although sound does it too, right? This is, sound can reflect off of walls. Sound can refract through air into water. It's not as dramatic as light is. Resonance is a very sound-based phenomenon, though. So if you're asked questions, just right now be able to identify. I'm going to do one more thing here, and it's related back to these. I'm going to mention some equations here, and I'm actually going to pull up your reference table. I'm going to look for waves. All right. Now, again, you should notice that the wave section has there are more than, yeah, okay, that's fair. There are far fewer equations here in the wave section, because it is mostly conceptual. It's mostly understanding like relationships, understanding visuals, what would happen if type stuff. But there are some things that are strictly number questions, so I'll go through a few of these, right? You should notice a couple of symbols that you recognize. Not too. There we go. F for frequency, T for period, lambda for wavelength. There is a V for velocity, right? So you should remember that I said up here that, where did I say it? Oh, there it is. T and F, frequency and period, have an inverse relationship. I also said that wavelength and frequency have an inverse relationship. They are two different equations. Right here, velocity is frequency times wavelength. Remember, so velocity is measured in, let me get a smaller pen out for this. Velocity is meters per second. Remember that wavelength is measured in meters, and frequency is hertz, or 1 over seconds. If you take 1 over seconds times meters, you get meters per second. This one is interesting. The period is measured in seconds. Frequency is 1 over seconds. So 1 over seconds is seconds. An alternative of this equation, by the way, is that 1 equals the frequency times the period. That's always true. Frequency times period should always equal 1. I'm going to look back at one of the examples I did here. If you look, the frequency of B here was 2 hertz. The period was half. 2 times half, 2 divided by 2. That's 1. The frequency of wave A was 1.5. The period was 0.67, or 2/3. Well, this is 3 halves. 3 over 2 times 2 over 3. That's 1. Frequency times period should always be 1. So there's a nice relationship there. You should also notice the angle of incidence and angle of reflection. Well, look, there's that equation. That's an equation they give you. I'm not sure why. It's more conceptual than anything. But right here, right, the angle of incidence and reflection for a mirror are the same. Right, and I'm just going to kind of focus on those 3 for a little bit here. Like I said, there's okay, no, it is. There are 2 more equations. I don't know what this equation's all about. Not worried about that last bit. But these 2 equations. I'll get to those next video, but we'll focus on the top 3. Really the top 2, because again, this is a visual. The fact that the incident angle and the reflected angle are the same, that's more of a visual. Just remember that if it comes in at this angle, it will leave at the same angle. If it comes in at this angle, it will leave at the same angle. Frequency, period, and wavelength, and velocity. So, let's see. Example question. Quick example question. Hello? Alright. Okay. A sound wave has a frequency of 512 hertz. What is its wavelength? Right, so we're given information about the frequency. It is 512 hertz. I want to know what is the wavelength. I have no idea. They only tell me it's a sound wave. Now, the only relationship that I have, or that you have in your reference table, is that v equals f lambda. And that would be great. Frequency is, or velocity is frequency times wavelength, which would be great if I had the velocity. They did tell you it was a sound wave. And there are lots of constants on the front page of your reference table. And one of those constants is the speed of sound at STP. Oh no, STP? We're only ever going to work at STP, so don't worry about that. But the speed of sound is 330 times 10 squared meters per second. It's 331 meters per second. That's pretty fast. So, I actually do know one more piece of information. I know that the velocity is 3.31 times 10 squared meters. Oop, don't do that. There we go. Per second. So I can do v equals f times lambda, which is 3.31 times 10 squared meters per second equals 512 hertz times lambda, and I can divide both sides by 512 and get that the wavelength is not super long. My phone, my calculator. What are you doing? There we go. Sorry, that was weird. 331 divided by 512 is 0.65. 0.646. 646 meters. Again, wavelength is measured in meters. It's a distance. It's how long is the wave. So the wave is 0.646 meters long. That's, again, pretty quintessential example. Second example, same idea. A light wave has a frequency of okay. I was going to do a question, but I really just wanted to do this to tell you about another thing on the front page, so I'm just going to tell you about the other thing on the front page. You don't just have the speed of sound, you also have the speed of light. The speed of light in a vacuum is 3 times 10 to the 8th meters per second. Air, for our purposes, is functionally a vacuum, so this is also the speed of light through air, 3 times 10 to the 8th meters per second. It's very fast, 300 million meters per second, which is why light from the sun gets here in like 8 minutes. 7 minutes? I don't know the exact math there. But it's c, right? A lowercase c is the symbol for the speed of light. So if you have to do something with a light wave, but they don't tell you how fast it's going, it's not because they don't want you to answer the question, it's because you have it, right? It's down there on the reference table. So, there's that. As far as frequency and period, it's not... You might get a question like, you sit on a dock and count, I don't know, 20 waves pass in 8 seconds. What is the frequency of waves hitting the dock? Right? So, again, fairly typical. Sit on a dock, count 20 waves pass in 8 seconds. What's the frequency? Well, frequency is how many waves go by in 1 second. I know 20 waves go by in 8 seconds, so I should take 20 divided by 8. So 20 waves divided by 8 seconds is 2.5 waves per second. It's not how you spell second. Or 2.5 hertz. Waves per second is probably a little more accurate, but 2.5 hertz, right? It would be things like that. You could also be asked, what is the period of the waves hitting the dock? In which case you could do this and then do 1 over that, or how long does it take for one wave to go by? So you do time divided by waves. 8 divided by 20, which is 4 over 10, which is 0.4. So the period is 0.4 seconds, right? It takes 0.4 seconds for a wave to go by. Yeah. All right. There's not a ton more to waves, so we are going to have a quiz. Probably, you know what? It will probably only be 2 sets of examples. There's probably one set up already. There might not be a set up already, but if there's a homework set up already, it probably has to do with this information and this, right? There'll be one more set of questions based on kind of the rest of this. There's also one more like extra wave interaction that I'll talk about. There is another simulation that I can pull up, so I will do that when I get to it. But until the next video, I will see you. If you have questions, email me. Let me know. Carrier pigeon. One day somebody's going to send me a carrier pigeon. I'm not going to know what to do about it, but until that day comes, I'll keep saying it as a joke. Anyway, take care of yourselves, kids. Be good. Stay safe. And like I said, until next time. See ya.